Robot makers, if you were gifted 2 robot arms, what would you do with them? I'm really interested to see what you would make of these. Definitely put in the comments what you would do if you were gifted 2 of these. So if you're interested to see what a Waveshare RoArm robot arm can do, then this is the show for you. So let's dive straight in. My name's Kevin. Come with me as we build robots, bring them to life with code, and have a whole lot of fun along the way. Okay, let me get over to my keynote. And hopefully it will work. There we go. Yes, so I've been gifted 2 robot arms from Waveshare, and I thought it'd be quite a fun show to do, to talk about what these can do, and also a bit of an interaction with yourselves. What would you do if you were gifted these? So I've been given the RoArm M2, which is a 4 degree of freedom robot arm. I've got one of these on my desk, and one of them is attached to another robot I'll show you in a second. And I've also got a RoArm M3, which is the 5 degree of freedom version of that robot arm. You can see there they range from $189 to $239. And that's just to get started. Now these are fantastic robot arms. I was so pleased when I was gifted these. I'll go through a couple of the features and then we'll get on to a bit of a demo what we can actually do with this. So these are very expandable. They have this customizable EAT, which is the end of arm tooling, so you can change that out. So instead of just being a gripper, you can put like a camera on there, you can put whatever you like on the end of it. Very easy to use, so it's cross-platform. There's a web app that you can connect to. It has an ESP32 processor, ESP32 MCU, so you can actually connect to the Wi-Fi of that chip and you get a nice little web page. You can control the arm from there. It's got 360 degree rotational base, so it can move completely around. It can whack you in the face if you're not careful. I've had this happen to me when I was setting this up. I inadvertently made it sort of slam and it nearly gave me a black eye. It's open source code, so all the source code documentation for the RoArm M2 and M3 completely open source. Makes it very easy for you to develop further. And it's very lightweight structure, so it's made of this carbon fibre and 50-52 aluminium alloy weighing under 850 grams. So it's quite chunky to lift up, but that's most of the weight is actually in the base to give it some structure. The actual arm itself is quite lightweight. It's got this joint drive design, so there's 12-bit magnetic encoders inside each of the servos, and that means that it can detect where it is and then feed that back to the controller, which is quite key. We'll have a look at that in a minute. It means we can actually do a learn. We can move the arm, record the position, and then have it go to that position. We do all that kind of cool stuff. Yeah, dual drive technology, so to increase the shoulder torque, they've actually got 2 servos side by side to give it that extra kind of power, and it's driven by this powerful ESP32 processor, so you can get the Wi-Fi interface to that. You can also connect direct over USB or through UART, whatever you prefer. It's compatible with things like ROS 2, so if you're into sort of serious robotics, very easy to have this working with ROS as well. I believe this will also work with VM as well if you're interested in that. And there's a whole of rich tutorials, graphic tutorials, videos and so on to get you up to speed with the arm. So plenty to get your teeth into there. So here you go, there's a little bit of a graphic eye pinch from their website. So I've got the desk clamp version here, so I've just attached this one to my desk. The other one, grab this. This one I've attached to a VM robot, little rover that they have. This is the M2. You can see there we've got the little clamp on the end, and I've even attached a Raspberry Pi camera and a Raspberry Pi Zero to this one as well, so this can hook up, and at the moment it's just attached. I've not got this wired up. Put that back there for a second. So you can see there some of the rotational angles that this can achieve. It's pretty flexible. It can pretty much do whatever you need it to do. Oops, sorry about that, my microphone flipped over there, you might not have heard some of that. So yes, some of the features, it's got Wi-Fi on board, it's got a nice little antenna on the base there. There's an OLED display, so you can actually see the IP address of the that it's connected to or that it's broadcasting from. You can see whether it's in access point mode where you can connect to it, or if it's in Wi-Fi station mode where it attaches to your router and gets the IP from there. Has an LED, which is really cool, so it's got like a workspace LED. It's quite bright as well. We'll have a play with that in a second. So you can switch that on, you can actually see what you're working on, and if you've got a camera on the end as well, it will illuminate whatever it's pointing at. You can also see on there as well that it has the 40-pin header, so you can connect to Raspberry Pi Pico, Raspberry Pi like 4 or 5, I assume, underneath that, and connect directly to it. But I'm actually connecting to my Mac over a USB cable for this demo today. You can see there's some attachments that they got on the end of the arms there. So these arms are these, is it the 52, it's a bit like 2020 extruded bar, but it's slightly different there. And that one, yes, you can connect these mounting points to it, and I've got the Raspberry Pi Zero, just like they've got there, attached to one of mine, so you can actually drive the camera from it. And there we go. So this is the lineup. We've got 3 of the robot arms from Waveshare. We've got the RoArm M1, the M2 and the M3. So the M1 is the first one that they launched. They did the M2 a couple of years ago, and then the M3 I think was just last year. So I've had these, they sent these just before the M3 was launched, so that's how long I've had these and not been playing with them for. And you can see there that between the M2 and the M3, the extra degree of freedom is in the wrist. So there's like an extra servo there just to give it some extra flexibility in the wrist. So if you like these videos and you want me to make more of these kinds of videos, please give this video a like, drop a comment, let me know what you would do if you had 2 robot arms gifted to you. And if you're not subscribed to the channel, please subscribe to the channel. It means so much to me when people do that. So I do go live as well every single Sunday, apart from the last 2 Sundays. I was on holiday and then I was actually sick last Sunday, so apologies for that, but I do go live every single Sunday that I can. Okay, so serial servos. I've got a bunch of serial servos here with me on my desk, and I've also got a little driver board, so we'll have a play about with that in the demo section in a minute or two. But I just wanted to sort of call out the differences between these and the kind of hobby servos that we've typically used on other projects. These are quite different, and you do tend to find these in more serious robotics builds. So this robot that I have, which is from Electfreaks, this is their X-Go Lite robot dog, and this one has these servos in there as well. These are the serial servos, and we'll get into the differences between regular kind of hobby servos and serial servos. So let's have a look at some of the differences. So on the left we've got the typical pulse width modulation servo that we're probably all very familiar with if you've been building any of the robot projects that we've done in the past 4 or 5 years. And then on the right are these serial servos, which I've not touched before. In fact, these ones that arrived literally hours before the show are my first serial servos that I've actually bought myself. These just happen to be Waveshare as well, because why not? So let's have a look at some of the features of the serial servos versus pulse width modulation servos. So to control a PWM servo, you just need a pulse width, which is typically, you have 1 pin per servo from your microcontroller, and you will send a pulse width signal. So it's essentially like a square wave signal. We'll have a look at that in a minute. And the distance between the sort of peaks and the troughs, that defines what the pulse is, how quickly you're sending this. Serial servos, on the other hand, they require a digital packet of information. We'll have a look at what one of those looks like in a minute, and they usually send those over UART, RS485, CAN bus, and so on. So there's different standards. It's not quite as straightforward as the pulse width modulation ones, but with that control we get so much extra. So wiring wise, pulse width modulation, we need 1 control pin per servo. Whereas with the digital servos, you can actually daisy chain them together. So you can have one connected to another, and it makes the wiring very, very simple. And you only need that 1 pin to actually control all of the servos. You can have up to 253 servos on there. So addressing on a pulse width modulation servo is based on the physical pin you're connected to, whereas on serial servos you actually have to provide a unique ID, and then that's stored in the EEPROM of the servo itself. So one of the things I've not done yet with these that I bought is giving these an ID number. So we'll have a play around with that in the demo in a little bit and see where we can get with that. Feedback wise, pulse width modulation servos don't typically provide feedback, so you send them a signal, they move to that position, and then you just trust that that position has been achieved. Whereas serial servos, they can actually provide feedback on the position that the servo is actually in, the amount of torque or load that joint is under, how much voltage is being used, the temperature of the servo. There's all this kind of extra data that you can get back from each of the servos, and that means we can do some really clever things with our robot arms. If we can get feedback, we can actually do a kind of teach kind of program where we move the arm with no torque, so it's just free to move the actual servos. We can capture the position of each of the servos, and then we can record that, and then we can actually play that back and it'll move to that position. So we can program our arm very, very simply. I've got a nice little test program to show you that in a minute. So feature-wise, basic control pulse width modulation servos, they can just do, you tell it where to move to, it'll move to that. Whereas with the serial servos, we've got this kind of advanced torque limiting, speed control, smooth motion. We can do all these kinds of clever things with it that you can't do with pulse width modulation. Ease of use wise, PWM is probably way ahead. It's very, very simple. It's widely supported. You just plug it in, you send it a PWM signal, and it works. Whereas with serial servos, they require handling of protocols. You need some kind of library, and therefore they're a bit more fiddly to do. So in the 2 hours I had before this show started, I've not been able to get my servos working. But we have got the RoArm working. That's a different library, so we'll have a look at that. PWM servos are very, very cheap. You can buy a couple of them for a couple of dollars. They're not very expensive, whereas serial servos are significantly more expensive. There's a lot more electronics in them, and because of that feedback mechanism and the fact that it has to interpret this packet of information to control them, that requires a bit more electronics in there. So PWM, they're probably best for simple projects, remote control cars, pan tilt kind of operations, very simple robots, whereas serial servos are more suited to more advanced robotics, multi-joint systems, diagnostics, things where you need that feedback. And scalability wise, you're only limited on PWM by the number of pins available on your microcontroller. So if you've got an Arduino or a Raspberry Pi Pico microbit, something like that, however many pins that has defines how many servos that you can attach to that, unless you use another control board like the PCA 9685 board, for example. Whereas with serial servos, you can have many servos controlled by one line. So as many pins as you could actually have separate buses for each of those. But in reality, the things that are going to limit you is the amount of power that's required to drive them, and also the more servos that you have in that bus, the more noise there is, if you like, on that channel. So it has to each servo has to listen and then respond back if it's spoken to. The more that you have on that will limit the amount of communication cycles you can have. So it's kind of the speed of communication. So let's have a quick look at how PWM servos work. This is a couple of slides I've shown on some previous things, so if you've seen these before, you might be able to fast forward this bit. So a typical servo has servo horn, a shaft, mounting points in the connector, and on a PWM one, that's the 3-pin connector. So you've got the middle one is the signal, no, the other way around. The middle one is the power, the orange one is the signal, and then the brown one is ground. And the idea is whichever way you plug that in, you can't power it incorrectly, because of the way that the power is always in the middle pin. If we look inside the PWM one, so we've got this little gearbox, got a potentiometer, we've got a little control circuit, and we've got the actual DC motor that does the turning of the servo. So this is going to look very, very similar in a serial servo. That control circuitry is the thing that will be slightly different, and the potentiometer might be a slightly higher quality one, because we actually want to know where the servo is pointing at, so that will be probably a higher quality potentiometer. Here's one I disassembled earlier. As you can see there, you've got the little control board, you can see the motor there with a little sprocket on the top there, a little gear on the top, and then there's a gearbox that just helps provide a bit more torque to the servo. And this is how the pulse width modulation cycle actually works. So you will change the pulse, you'll send a high signal and then drop to low, and it's typically about 5 volts between the sort of top and the bottom of that signal. And the duty cycle is that area, just let's get my mouse out there, this bit here. So however long the signal is on for, that's kind of an on, and then when you drop it down to the off position, that's the rest of that particular cycle. So you can see there, if we wanted to send to 0 degrees, we would send a 1 millisecond duty cycle signal, and then there'd be 20 milliseconds to the next peak, the next signal. So it's always going to be 20 milliseconds between the cycles. If we want to go to 90 degrees, then it's 1.5 milliseconds, 180 would be 2 milliseconds, would be twice that duty cycle there. So you can see that's kind of how it works, 20 milliseconds per period, and that's 50 Hertz. So that's how a pulse width modulation works. It's quite straightforward, and microcontroller is very capable of doing this. So Raspberry Pi Pico, for example, you could have one of the, I think you could have one servo on each of the GPIO pins, are all capable of doing that. So let's have a look how serial servos work. So these work slightly differently. So you send a data packet. So this data packet is made up of a number of different bytes. So the first 2 bytes are the header. So this FFFF is what you would look for to see, is this the start of a packet. Then you've got the actual servo ID. So this is 2 bytes, sorry, 1 byte, and that 1 byte will be between 0 and 253. 254 has been reserved as a broadcast packet, so that means all the servos that are connected in the chain will receive the same packet of information. Otherwise, the servos will just sit there and they'll wait for their number to come up, and then they'll react to that. Next up then we have the length of the instruction plus the parameters plus the checksum. So this one says it's 5 bytes long, and if you look at the remaining number of bytes, so this 1, 2, 3, 4, 5 is the number of bytes in this particular instruction. We've then got the write data instruction, so 03 means write this data to the servo. It's going to say this is the address, which is the goal position, so where do we want to move to. And then we've got the value, the center position is 512, so 0002 for that position. And then we've got a checksum, which is essentially we add up all these different parts of the signal, and then we define a number based on that. It's a very simple kind of hashing thing, and it just means that we can see if the signal has been overwritten by another signal from another servo, perhaps that was giving some feedback. And it's just a way of making sure that the whole packet is valid. And we can actually daisy chain these together, so they do simply connect to each other. You might have to have something like this. This one is what the Waveshare one came with, so it's a little splitter cable. And what we would typically do on there, if I just pull these out, plug this in like so. Pull one off that as well. This makes the wiring very, very straightforward, because it's just one big long chain of cables, and you can see there we've got 2 servos, and then the last one will connect up to the little controller board that we have there as well. So this is a little special board that you would need in addition to the servos themselves, just one of these per bus. You can see there we've got 2 servos connected to the same connector. And that just requires 1 pin going back to the microcontroller to connect to. So it's a bit more involved. We have to send packets of data like this, and we can also tell the servo to give us feedback, and it will return a very similar kind of packet, and it will actually show us the data that it's received there, such as what the current position is, the temperature, and so on. So there you go. So we don't need to have 1 GPIO pin taken up per servo. We can just have 1 pin that can connect to all those serial servos via this little control board. So that's the only extra piece of information that I probably didn't give before, is that you actually have to have this little control board to make the serial servos work. But they can provide feedback on current position, temperature, the torque. We can tell it to turn the torque off, which means make the servo unpowered, so we can then move it without sort of straining against it, trying to hold that position. And we can see there one pin on the microcontroller can control up to 253 servos, and that address 254 is reserved for the broadcast, move all the servos at the same time. And the update speed and power are the only limiting factors, so how quickly we can send out commands over that bus and how much power we can drive through that bus will be the limiting factor, because if they're all connected to the same power as well through those 3 pins, then you're limited by how much power you can actually send down that tiny cable. Okay, so let's have a bit of a demo, shall we? So I'm going to show you now on the desk here. I've got a slightly different view of this. Let's go for that view there. So the robot arm, I'm going to switch it off, and I'm going to disconnect it from the computer. So this is the robot arm here, and you can see there we've got the little grabber. I can grab hold of that, we can open that, we can close that. Can I rotate this round? So I'm trying to show just here, this is where the LED is. We'll switch that on in a minute and you can see how bright that is. We can rotate the arm round like that. We can maneuver that. There's another joint there, so we can do all kinds of funky positions with this. Just disconnected that LED there. Let's put that back in. And if I power this up, it will do a little dance for us. It'll basically just initialize itself. So if I press the power, it'll raise up the arm. It'll then go to its kind of default position. So if I was to open up all those different, if I moved each of the servos, it would then reset to this position. I'm just going to plug this in. Bear with me. Okay. So what I'm going to do now, I'm just going to go back over to, let's try that one here. And I'm just going to load up Visual Studio Code. Just going to press Control C on there for a second, and I'm just going to move this down to this window here. No, it's just, let me just set up my screen correctly here. So I want that screen there to be the bottom screen, which is it that one? Yep, it's that one. Secondary display, okay. And I'm just going to move that out of the way. Move this down a little bit. I'll show you the code, but then I'll show you the code running and then I'll show the actual code itself. So let me just get this up and running. So what I need to do is just run this. So this is teach playback. So it's connected to the arm and it's going to ask me to maneuver that arm now to a position. So I'm going to move it. Let's go to the other camera again. You can see me there. I'm going to move it to this position here. I'm going to turn around the arm. I'm going to open up the little grabber a little bit. And I'm going to move the arm like that. I'm then going to press space, which will record the position that we've just set. There we go. If I now do another one, so it's kind of like that. Press space again. There we go. It's recorded that position. And I'm going to move it over here. I'm going to close the arm. Rotate that round a little bit. I'm going to press space again. Okay, and then what should we do next? Let's make it go like that. Press space again. Right, so I've got 4 positions recorded. I'm now going to press R for return to its kind of start position. Okay, so we can just see that it's returned to its start position there. I'm going to press P for play, and this should now play back the movements that we've recorded. So let's see if it'll do that. So it's moving it down now. It should open up the little end effector as well. So I'm going to do the other position we asked it to do. So I'm going to move over there slightly, closing the arm, and that was the last position we had it to do. So then I'm going to go to its default position, and then what it's doing now is it's turned off the torque, so there's now no torque being provided to the motor, so I can move this around however I like. So if I just press Q for quit on there, there we go, we've quitted the program. So I'm going to show you the code and we can quickly run through how this actually works. Okay, so this is a really simple program. You can see that it's going to turn off the torque, which means it's going to, there's going to be no power going to the servos, but it will still be sending back the position information where they are. We can press a button, which is the space bar, to record the current position. It's automatically going to return to the home position once we've finished all these, and it'll gently move to the recorded position. Gently move, I think we will require a little bit of work on our code to make that a lot smoother, because it does seem to jitter a little bit as it goes along there. So this class teach playback controller, this one is going to take in the serial port that the serial servos are connected to. So on my Mac this is dev TTY USB-110. The baud rate is how quickly it's communicating over that UART, and then we're going to set up that UART just doing these commands here. We're then going to set the home position So this is just a position that we've arbitrarily said is the home position, the X, Y. We've got the T, R and G, so these are the other parts of the robot arm. Let me see what else we've got there. So we've got some movement parameters, so the speed, how quickly it's moving, how it interpolates steps in between the different positions, and this step delay, so 0.1. We've then got a connection piece of code. This is going to connect to the serial port. It's going to connect to the SIR, which is our object that's going to represent the connection to the serial. We then say that the telemetry, we're recording information, that's true. We're going to have a telemetry thread for that. I'm going to start that thread. Then we're going to sleep until we lose that connection. If there's any connection failures, it's going to report back an error there. And then on disconnect, it's basically just going to disconnect from that serial port and free that up for anything else that might want to use it. Reading telemetry, then we're going to basically create a little buffer. While we're running, we're going to, and while the serial port is open, and while we're waiting for information, or waiting for information is greater than 0, so we pressed record. It's then going to record the chunk of data coming from the serial port, and then it's basically just going to increment that buffer each time we add a chunk of data to that. While it's not got a return, like a end of line character, it's going to split up those different characters. So if we press R or P or whatever, any of the commands that we're presenting it with, or in this case, it's going to split up the data packet that comes through. So it's going to get the X, Y, Z, the T, I, T, R and G, which is some of the other positional motors that are in here, and it's going to store them in that buffer. Otherwise, if there's an error, it's just going to pass on that error. Sending command will send the command that we provide it to the robot arm, and that's essentially how we play back that buffer. And then we can initialize the robot. So we've got some commands here. This T100 means return to the initialization position, the home position for the robot arm. We can also call that move to home, which is what we've defined as our home position. It's slightly different than the robot's defined position. We can turn the torque on or off, so this helps when we want to manually move the arm. We need to be able to turn the torque off, and then we want to turn the torque back on once we've finished with that. Record the current position will record exactly as you'd expect the current position, and we need to create a clean position record. So we've got the X, Y, Z, T, R and G. The tilt is the TIT there. And then we've got other things like record the position, and we just append that to the recorded position. So we've got a little array of positions there. We've got the move to home, so again that will just turn on the torque, it'll move it to the home position. So it'll set everything to our X, Y, Z and so on positions. Martin's saying it has a limp mode. His daughter's car had that the other week. So yeah, move to position, again we'll basically play back the positions that have been passed to it. You can just see there for each of those move commands it's going to set them and then send them to the arm. And then smooth move to position is going to use some interpolation, so it's just going to from the current position to the position, the home position, it's going to get all of those, and then it's going to go through and interpolate all the different steps, kind of make up a middle step between the steps that's been provided. Then we've got display recorded position, so it's just going to display that on screen. It's going to get the input key, so this is basically the commands that we're going to type in, and then we've got this nice little table there. So space will record a current position, R will return it to its home position, P will play back the recorded positions, L will list the recorded positions, C will clear the recorded positions, and T will toggle the torque on or off. Now we do have some other commands that we can send to our robot arm. We can actually send it commands to turn on the LED or turn that off. So I'm going to find out what that command is, and then I'm going to send it to it. So let me just bring up the list of commands there. So what we could actually do, we could do a bit of vibe coding here. Let's open up the chat, and let's say create a program to turn the LED on and then off after with a input key, something like that. just typing this just behind my head there. So I'm using the Copilot, and this is going to create a piece of code. It already knows how to program this, so this shouldn't take it too long to do this. And what it will do is it'll create, if I just go to that little one just there, you can just see I've just pressed return there. It's having to think about this. It's going to create a little test program to do exactly that. There we go. So I'm just going to give it a second to do that. I've written some other test programs over here for doing some movements, and I can show you as well, just because I took a picture of it, what the little display looks like. So it'll say AP RoArm M3, or if it's the M2 it'll say M2. ST is the access point mode, whether it's on or off. So the access point mode is currently off. I'm not connected to that over Wi-Fi, so I could connect from my phone, for example, to control the robot arm. I find the interface is pretty crude. There's some sliders that it provides, but if you do that, it'll sort of thrash around quite violently. So I'm not going to be doing that. And what else have we got? We have the MAC address, so that's like the IP address, not quite the IP address, it's the machine's hardware ID, but you can use that to find this if you've got like a router of your own and you want to find out what IP address has been assigned to it. And then it's also got this little status message RoArm M2 started. It's actually the M3 this, so this must be a quite early prototype firmware that they sent me on this one. I've not flashed it with anything else there. You can just about see the antenna base there as well. So just underneath this little board is the controller board, which is an ESP32 based microcontroller. Now that's taking way longer than I would have expected. I'm just going to stop that. I'm going to change that to ChatGPT, and then I'm going to send that again. Let's see if that runs any quicker this time. You can choose which AI model you want to have help you with your code. And this is this agentic AI, which is all the trend at the moment. So I'll give it another couple of seconds to do that. So Martin's asked, is that serial board needed, or can you send serial via GPIO? I believe you can send it by GPIO directly, but this board provides power as well. So it's saying cannot find USB. So which one is that? What's the name of that? Silver LED toggle. So all that's gone wrong there is it's the wrong USB modem, so it should be 110, I think. Let's just change that and see if that works. Right, let's try that again. Let's just do ls dev. Let's see what the USB serial -110. Okay, so that does look correct. And this, let me just tell it, this is for the RoArm. So you tell it a bit of information. I think he was looking at my previous command. I was trying to get these servos working just before the show, but I wasn't actually able to get them working. Shows you they're not quite straightforward. They don't come with a driver. You've got to kind of just figure that stuff out. Okay, so it's just going to add the RoArm M1 focus LED control with control script with joint. I don't need it to do any of that. I just need to turn the LED on and off. That's all I wanted it to do. Let's wait for it to provide that update, and then we'll run that code. So one of the things I do find about this kind of new style of coding, this vibe coding, is you do spend a lot of time waiting around for stuff. I am on the ChatGPT 5 Plus account, so I don't know if that makes it any quicker or slower. So turn the LED on. I'm not quite sure that's what I wanted. Let me just check on the RoArm code. Okay, so if I run this code, just see if I've got the think I might need to provide the port number, so let me do /dev/tty. What's the name of it again? Let me just find that. tty.usb modem. What is that? Just bear with me while I just find that again. I don't think it's dot, is it? I think it's just TTY. It is TTY.USB serial. There we go. Let's just grab that. Pass that as a parameter, and I think that should connect us to it. Nope, so it's not happy with that. Port could not be opened, no such address. Dev/ there we go. Right, so all this telemetry is being sent back. If I move this arm, if I pick it up and move it around, you can see all that telemetry. If I hold it still, you can see all that data is coming back live. So what I want to do is I want to send some commands to this. Thanks Dan saying it's USB serial, not USB modem. Yes, that fixed that one up. So what I want to do is I want to send some different commands to this. So let me just get a list of RoArm commands. 2 commands. And I'll show you how we actually send commands. So with this RoArm, you send a JSON block, and you send a command and a value. So T would be like move to position, like to a particular position, or you could tell it to turn the torque on or off, for example. So let's try that torque on and off, for example. Let's try that one. So if I send, the thing is, it's sending all these commands so quickly that I can't actually see what I'm typing. So if I update this, so instead of just spurting out all that stuff, let's make it so, yeah, we don't have that print. Let's just hide that piece of code there and run this again. Okay, so if I now type in, so it's brackets T, and then the command itself, I think. Is that right? Or no, do we actually send a command and then torque? I think that's right, torque, CTRL, and then I think we send a value. So let's a value of a 0. Let's see if that's done anything. Let's do that same command again, but this time send a 1. Nope, that didn't work. Let me find where the commands are on here. I'm pretty sure I've got one where I've previously created this. Rather than me trying to hack this together live on the stream, I want to show you one that actually works. That would be really cool. Let's just stop that again. So yeah, so the way that you interface with this RoboArm is kind of Waveshare's way of doing this. So you have to send a JSON object with a command and a value, and you can send multiple commands to move different servos in one of those strings. So you can build up quite a complicated command to send in one go and then get all that telemetry data back as well. But what I want to try and do is just literally turn the LED on and off. So let me be really specific in this this next code run. I'll just type this over here. So update the LED toggle so that it turns the RoArm M2 arm LED on and then off. Also toggle the torque on and then off for the arm. Right, let's see if it understands that. There we go. I'll give it a couple of seconds to go through that, and then we'll probably just have another play with that. In fact, the torque is on. The last command that I did actually work. So the arm is absolutely rock solid and I cannot move it. So that last one that we sent with the torque 1 did actually work. So if that works, where's the command for the LED? Let me find that. So that's real funny that didn't seem to work, but it actually has worked. Anyway, it's updating the code. It's going to update the LED. Let's see if it's got that up and running now. It's interesting to see the code it's actually sending there. Right, I'll allow it to run, see what happens. No, it says the LED should be on and it isn't on, so that clearly didn't work. Right, I'm just going to find the actual command that we need to send. I think it's LED on. Was it LED control? Let's see. For LED. I'm just tapping this on another screen off to the right. There we go. Oh, so it's T114. Right, let's just run that previous command then. So let's run the one where we... Which one was it? It's the RoArm one, wasn't it? Let me just run that one again. With the... Right, so if I send brackets T and then 114 and then LED and then a value like 255, let's go to the overhead like this, and I'm going to switch off the overhead light if I can do that, just so you can actually see the LED come on. Of course, when I want to do that doesn't work. Right, so if I turn the desk overhead light off, of course that's taking ages to do. I'm going to send the command anyway to turn this on. Let's see if I can get that to work. Oh, I didn't close my bracket. Let's try that again and then send the whole thing correctly, because I didn't close the bracket. There we go. That hasn't actually turned it on. Let's try. Make sure I've got that right. So T114 and then LED and then 0. Let's try T114 LED and then 0. T114 255. Yes, that's come on. You can see the LEDs come on very bright. So let's try do that a little less bright. So T:114 LED, and then let's try 128. So it's kind of half the value. Looks exactly the same to me. I think it might just be on or off. LED and then 0. I'm terrible at typing these commands out. I'm not great at doing a raw JSON. Let's try that again. So :114 LED and then 0. There we go. That's worked. So if I try that one, should turn it on. Let's try the full value. Yep, it's come on now. Bit of a delay in it reacting to that, so then we can turn it off with that other command just there. There we go. That seems to be working okay now. So they're the commands to turn the LED on and off. And if we want to turn the torque on and off, we know that one. We did that one a second ago, so it's We scroll up, we can probably find that one perhaps at the top of our code, unless it's scrolled off the very top. No, I'm just going to scroll off the very top. So it was something like torque control, wasn't it? So torque. That was command torque. So cmd underscore torque underscore ctrl, and then, well, actually you can just send cmd instead, cmd 200, 210 even, and then the value, and then 0. Give that a second. So there you go, I can move the arm around very freely. So if I now do that same command and 1, it still let me move it around. So I would have thought that would, there we go, it's locked it, I can't move it. So it just takes it a couple of seconds for it to process that command for whatever reason. Turn that off again, and it should just droop to the desk once it's figured out that that's the command I've told it to send. There we go. Cool. So it's a bit fiddly to program over the serial, and it's literally taking that JSON string as a text string, and then the ESP32 is interpreting that string as JSON as a command, and then moving the servos, or switching the LED on and off, or turning on the torque or not. You can even enable, disable the Wi-Fi using the commands from Waveshare. So there's a whole bunch of different commands that you can send to this robot arm. So my question is, given I've got 2 of these, what should I do with them? Should I have 2 of these kind of robots? I've actually got 2 of these VM robots. There's another one, so I could bolt the other one to the top of that and have kind of 2 dueling robots. I could make it play the piano. Maybe not quite play the piano. I could make it have some little end effectors, so it can perhaps press a key on a piano or something like that, but it would probably require quite a lot of code. They're quite accurate, so it can move around. Did it say it was 0.08 of a degree accuracy? So you can move the hand to a position, teach it that that's where a particular key on the keyboard is, for example, and then you could, teach it how to press down, pull the finger back up, and then move to the other ones. You could probably get that to work. That might require a little bit of teaching, but you could do that as long as you don't move the keyboard. If you move the keyboard, I think all bets are off there. Cool. So let me just go back to me for a second. What else did I want to show you on that one? I think that was everything on that particular demo. Let me have a look. Yeah, so it's basically just go through that. So like I said, I've not been able to get these working just yet. I think it just requires a bit more fiddling around. So sending those JSON commands, that wasn't specific to this little board. That was to do with the Waveshare RoArm robot and the ESP32 firmware. What we'll need to do on these ones is just send that FFFF and then the command over the serial. But before we do that, we actually need to program these so that this is, serial servo 0, this is serial servo 1, and so on. Because when they come out of the box, I think they're all represented as serial 1. You can see their Waveshare SC09 instead of SG09, and that's the serial servos. Cool. Let's get back to, that says piano playing robot arms would be amazing. Have you ever seen Short Circuit at the beginning of the film? Yes, that's something that happens on there if I remember correctly. There we go. Cool. So yeah, I've got 2 of these things. What should I do with them? Let me know in the comments below. I really want all of your ideas on that one. And if you've got any projects you want to share, the best place to do that is on our Discord group. So head over to kedrobots.com/Discord. You might even be able to see some pictures of Alex's cats. I don't know if she's put those up yet. But she's got 2 new cats, Solaire and Spooky. You can maybe be able to see some pictures of that in the pets area. If you've not uploaded pictures of your pets on there, you definitely need to do that as well. So head over to kedrobots.com/Discord for a free sign up link. Cheers. check your junk mail if you don't get it after a couple of minutes. If you're going to follow me on social media, I'm on all the social platforms. I'm at Kevin McAleer at threads.net. On TikTok, I'm at Kevin McAleer6. On Instagram, at Kevin McAleer. On X, I'm at KevsMac. On Mastodon, at KevsMac at mastodon.social. And I'm also on Blue Sky at kevsmac.bsky.social as well. So if you're not following me on there, give me a follow, say hi, share a picture of what you're currently working on. It'd be really cool. If you want to join me as well, you can do that a number of different ways. If you want to help support the channel, a number of people have done that. Head over to kezrobots.com/coffee. You can also do a super thanks or super chat in the YouTube chat window. And you can join the YouTube membership program or the Buy Me a Coffee membership program as well. So lots of different options there. And let's give a shout out to some of those people who have done exactly that. So over here on the left hand side, we've got the Buy Me a Coffee crew. So we've got Alan Whitehouse, who bought me a coffee, and Tom, who bought me a coffee in the past month. Member wise, we've got an anonymous member, we've got Silicon Fiber, Marie TKD, we've got Jeff Johnson, Deanne Corty, Marlene Brent, and Tom. Thank you all for supporting the show. I really do appreciate that. And then over here on the right hand side, we've got Dale from Hybrid Robotics. Hey again, Dale. We've got Oxrad39, Warren Packard. We've got Brian TW, Pierre's. Is it Balochet? We've got Bert. I'm terrible at names. We've got Bert. We've got Marie. We've got Michael, Steve, Ford, Bello, Johnny, Stephen, John Paul, Cassie, Johnny, and we have Tom as well. How's your arm doing, Cassie? Hope that's getting better now. Cool, so thank you everybody for supporting the show. It means so much to me that you continue to do this. I really, really do appreciate it. And it does mean that I can buy things like these are rather expensive servos. I think these were £20 for the 2 servos. Normally these are like $1 each or something like that. So $20 versus $1. Just shows you how much more expensive these are. And I think this was about $9, thereabouts £9 for the little Waveshare board, just out of interest. So there we go. You help me continue to do things like that. Cool. So if I go over here, oops, that was an interesting view. The little spinny logo tells me that it's at this point in the video that YouTube will be recommending over here another video from the 420 odd videos we have in the back catalogue that it's handpicked just for you. So definitely binge that video. Let me know what you think in the comments, and let me know what you would do if you were gifted 2 robot arms as well. Keep it clean. That's all I can say. Cool. So thank you so much for watching, and I shall see you next time. Bye for now.